is KCarmichael, and I'm going to be speaking with you today about solving one-step equations. Now, this is going to be a review for some of you who maybe haven't been in school for a while, or at least haven't been in a math class for a while. Or maybe some of you who struggled with algebra, or perhaps pre-algebra, or some other math class along the line. But don't worry, you can absolutely do this. The first thing I would like to speak with you about today is vocabulary. A lot of people don't realize that math really is its own language. And like a lot of fields where you have specialized terminology like maybe welding, nursing, computer science, in math we use special terms or we use general terms in a specialized way. Now I would recommend, and this is for everybody, but especially those of you who maybe have struggled with math sometime in your school career, I would recommend that you set aside a place to write down your vocabulary words. You should write down the terms, the formal definitions, and then a definition in your own words so that you can really begin to process it. You can keep this in a little notebook or a couple of sheets of paper in the front of your folder, whatever works for your organizational system. But you should keep it someplace handy so that you can refer to it anytime you run into a term that you're not that familiar with, whether it's in a lecture or in a problem or instructions to solve a set of problems. For those of you who would like extra retention and cognitive ability points, try writing it longhand. Old school with a pen and pencil or pen and paper. This will help you retain it over the long term better than if you type it into a computer. In fact, there was a 2010 Indiana University study that confirmed students who write longhand, especially in symbolic languages like mathematics, retain much better over the long term than those who went ahead and typed it into a computer right away. Alright, the first word I would like to talk with you about today, and this is one of those words that is a general word but used in a specialized way, is term. Now in mathematics, a term is a single number or a variable or a group of numbers and variables that are multiplied or divided together. Terms are separated by addition and subtraction signs. So let's have a few examples. This is a term. It's a single number. This is a term also. It's just a single variable. Terms can contain multiple numbers and variables that are multiplied together, like this term. This term is 85x to the 10th, y to the 8th, a to the 4th, z squared. Numbers, variables, all multiplied together. But you know what you don't see? Addition and subtraction signs, because those would indicate separate terms. This also is a single term, because all you see here is multiplication and division, not addition and subtraction. This indicates two separate terms. You have the x term and the 1 term, and they're separated by this addition sign right here. When you see that, you know you're dealing with more than one term. This has 2 terms. This one has 3. See, the terms are separated by addition and subtraction signs. That's how you know you're dealing with more than one term, whenever you see them separated by addition and subtraction signs. Alright? Let's go ahead and look at another math vocabulary word. This word is expression. A mathematical expression is a phrase that contains one or more terms. So, for example, this is an expression. It's a single term. It's a one-term expression. This is an expression that has 2 terms, 5 and a minus y squared b. It's all one expression. This is an expression with multiple terms. You see division, you see multiplication, you see addition, subtraction, but it's all a single expression. As is this. Once again, we have a two-term expression here. The first term is 14x cubed y squared a. The second term is 12x, but it's all one expression. Alright, last one. This math term is equation. Equations are different from the other ones that we've been dealing with. A mathematical equation is a statement that two expressions are equal. This is the key to the term equation. If it doesn't have this, it's not an equation. This is a simple equation. You see here, one expression, it's just a single term, a single variable, set equal to another expression. Again, just a single term. This is a more complicated equation. Here the expression is much more complex. X to the fourth minus 57 all to the power of 3. It's set equal to this expression, which is just a single number, 201. But the key is right here. Anytime you see this, you have an equation. So let's go ahead and look at some specific examples of equations. I'm going to try and give you an intuitive understanding of single-step equation solving here. This is just a simple balance. Push down on one side, the other side goes up. And I'm going to use it to model an equation. This is going to be our x. We don't know how many counters it contains. It's an unknown. And we're going to use it on this side to represent our x. I'm going to go ahead and add on this side also 3 counters. On the other side of our equation, our balance, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oops. Don't want to stay on there, do they? Now, we know that our equation is an equation. It's equal. It's balanced. See? The yellow pointer indicates that it's balanced. We know it's equal. But we still don't know how many counters are represented by our x. So how are we going to solve that? Well, on the balance, one way to simplify matters would be to get rid of these 3 counters on this side. But there's a problem. If we get rid of those 3 counters, it's not equal anymore. The way we deal with this is by doing the same thing on the other side. If we get rid of 3 counters on this side of the balance, all of a sudden our equation is equal again. Now we have our x, represented on this side by this, and 10 counters. We had 13 to start with, and we took away 3, so that's 10. So we know that this x is represented by 10. It's a 10 counter x. Alright, let's go ahead and take this to some algebraic symbols. So on this side, we had our x, and we had 3 counters. I'm going to represent that algebraically as our x plus 3. We know it's equal because it balances, and we had 13 counters on this side. To solve our equation on the balance, we removed 3 counters from each side. We represent that algebraically by subtracting 3. We did it on both sides because we wanted to keep it equal. Now 3 minus 3 is 0. zeros aren't necessary. So we have just x left on this side. It's still equal. And our 13 minus 3 is 10. X equals 10, which is exactly how we represented it on our balance. Our x and 10 counters. Now there are other ways to have a single-step equation other than to have x plus a number. We can do the opposite and have x minus a number. Let's go ahead and model that. So we have x. Let's subtract 4. And say it's equal to 6. Alright, so we have subtraction going on here. Up here we had addition, and we did the opposite. We had addition and we used subtraction to get rid of this 3 so that we could find x. Here we have subtraction. Let's go ahead and use the opposite operation, addition, to get rid of our 4. And once again, if you do it on one side of the equal sign, you've got to do it on the other side of the equal sign, otherwise it'll be off balance. So let's add 4 to this side as well. Now, minus 4 plus 4 is 0. All we're left with on this side is x. 6 plus 4 is 10. So we know that our x represents 10. It's equal to 10. So let's look at what's happening algebraically here. We had addition, and we did the opposite operation, subtraction, to simplify it. Here we had subtraction, and once again we did the opposite operation, addition, to simplify our equation so we could get x alone on this side of the equal sign. Now, addition and subtraction aren't the only two operations that are opposites. We have two more, and of course that would be multiplication and division. So let's go ahead and model that. Say we have a 2 multiplying x. The operation here is multiplication. And to undo it, to do the opposite, we need the opposite operation, which of course is division. We're going to divide by this 2. And once again, to keep the balance equal, we'll need to divide by 2 on the other side as well. Now 2 divided by 2 is 1. We have 1 times our x. 10 divided by 2 is 5. Here's where the trick comes in. 1 times x is just x. It's the identity property of multiplication. 1 times anything is the same anything you started with. 1 times 3 is 3, 1 times 5 is 5, 1 times x is x. So we don't need to write it this way. We can just represent it as x equals, in this case, 5. So what we did was we took multiplication and we did the opposite operation, division, and we did it on both sides. But just like with addition and subtraction, we don't have to start with multiplication. We can start with division. So let's look at it like this. Say we've got x and it's divided by 2. Now I'm going to go ahead and use a fraction representation of division here, but don't freak out. It's just division, and just like this symbol, it can be undone with multiplication. Okay? So if we've got x divided by 2 equals 5, we're going to undo this division with the opposite operation. That's multiplication, and we're going to multiply it times the same thing as being divided by here, 2. 2 times this. And just like all of these others, we're going to have to do it on the other side of the equal sign as well. So we're going to multiply by 2 over here as well. Now 2 divided by 2 is 1. We have 1 times our x. 5 times 2 is 10. And just like up here, 1 times x is just x. Just the same as 1 times 3 is 3, 1 times 5 is 5, 1 times x, it's just x. And in this case, it equals 10. Now I hope you'll take some time to practice solving one-step equations, and I have a couple of recommendations on how you can do that. If you go online to www.mathplayground.com/algebraequations.html, you'll find an applet that allows you to manipulate a balance much like this one and use it to solve single-step equations. Unfortunately, this site uses JavaScript. So if you're using an iPad or an iPhone, well, they don't play very well with JavaScript, so you're going to have to go to another site. www.khan-academy.org/math-e-step_dash-linear-equation-and-any-qualities-/y-of-intuition. This site will be entirely accessible from your iPad or iPhone if that's what you're using. I hope you do take the time to start practicing with these equations and manipulate them on your computer, because that'll really help you develop an intuitive feel for solving one-step equations, which of course will be a great foundation for solving other equations. Once again, my name is KCarmichael, and we've been talking about solving one-step equations. Thank you for your time.